Alright, we get to listen to another video by Miss Hewlin. Today we are looking at Lesson 3, which can be found in your textbook in section 7.3. Now yesterday we looked at 7.3 part 1, so today we're going to look at part 2. Not going to lie, this is one of the harder lessons and where most people make mistakes. We are dealing with a quadratic, so hopefully remember that from math class. And the quadratic has a lot of positives and negatives, square roots, and if you do one little mistake, it can carry through the whole equation. Okay, so let's make sure that we just go through these step by step, nice and slow, in order to make sure that you have the answer. So today's title is called the equilibrium constant. So we are going to have to do some equilibrium calculations. So we're going to organize our data with something called an ICE table. Okay, so the I stands for initial, C stands for change, and E stands for equilibrium. So we're looking at what the concentrations would be when they start, how much they're going to change by in order to get to equilibrium. We're going to let X represent the substance with the smallest coefficient in the chemical equation, which avoids fractional values of X. You're also going to look for perfect squares. Perfect squares will make this question a lot easier and you never have to do a quadratic. So always look for perfect squares. Remember though that you take the square root of each side to solve the equation. And remember that the square root of anything always has a plus or minus value. Okay, so you need to look at both values. Many problems do not involve perfect squares. So like I said, if you get those perfect squares questions, you'll see some of them in your homework. A lot easier to go through, but if we don't get those perfect squares, we're going to have to do the quadratic formula. Okay, so remember from your math class, the quadratic formula is ax squared plus bx plus c is equal to 0. So when you're organizing your data, you want to organize it in this fashion. So you have x squared terms all together, the x terms together, and then the regular terms by themselves. Once you have that, you can then plug them into this equation in order to solve for x. So recall that x is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. You do not have to memorize this. I will give it to you on quizzes and tests. However, you do have to know how to use it. We're going to come back to qualitative interpretation in a little bit, just because I want to focus on this quadratic formula first. So we're going to go straight to the example. So leave yourself a lot of room because it does take up a lot of space, and I want to try and make it as clear and concise as possible. So I'm going to make baby steps just to make it more clear for you guys. So like a very, very long question, it'd be worth a lot of marks, but high chance of error. Okay, so question says, COCl2 is an extremely toxic gas. It was used during World War I. Today it is used to manufacture pesticides, pharmaceuticals, dyes, and polymers. It is prepared by mixing carbon monoxide and chlorine gas in the following equation. It says we have 0.55 moles of carbon monoxide and 0.072 moles of chlorine gas. They're placed in a 5-liter container. At 870 Kelvin, the equilibrium constant is 0.20. What are the equilibrium concentrations of the mixture at 870 Kelvin? So remember, temperature is not changing here, letting us know that the K will stay constant throughout this equation. So kind of like we did in the previous part of this unit, I'm going to set up what is given in my equation. So I'm going to rewrite the equation. Remember, you need a lot of space for this question, so try not to take up so much, or you might be writing on a separate piece of paper. So it says we have 0.55 moles of carbon monoxide, so I'm going to put N is equal to 0.55 moles. And of Cl2, I have 0.072 moles. However, remember when we're dealing with these equations, right, we want to put it into the formula that we used yesterday where we had products over reactants so that we can solve for the X value. we need to use concentrations. And moles are obviously not concentrations, so we're going to go back to the formula. Remember, C is equal to N over V. So I see this 5 liters here, so I can actually divide this by 5 and divide this by 5. So when you actually put that in your calculator, you end up with C is equal to 0.11. And for your chlorine, you end up with 0.0144. Hey, look, I have wireless internet connection. 0.0144. Okay, so now we have the concentration of those. So at this point, we need to set up something called an ice table. So I'm actually, just to save space, I'm going to set it up off to the corner of what we just did. So for your ice table, you need to have I, C, and E. It's good to rewrite out your products and your reactants. So CO, Cl2, okay, so this is your ice table. You set it up like that. So remember, I stands for initial. So our initial concentration is what we just found to the left. So we know that the initial concentration of carbon monoxide is 0.11. We know that for chlorine we have 0.0144. And because this reaction is starting to take place, we obviously don't have any product. So your products in these situations will always start at 0. Okay? Little announcement, hold on. It's like you're really in class. So your products will always be 0 and your reactants will always be whatever the concentration values you found from the question. So at this point, we want to see how much it's going to change by so that we can figure out what it would be at equilibrium. Well, we don't know how much it's going to change, so we're going to give that a value of x. So reactants are only going to go down and products are only going to go up. So we're always going to give our reactants a negative x, and products will always get a positive x. So my reactants are going to change by negative x, which means I don't know how much. But if these reactants go down by x, my product is going to go up by x. So I put plus x. Okay, so try and start really wrapping your head around that. The reactants are being used up, therefore their only chance is to decrease. I started with 0 as a product, so the only thing I can do is go up. So that's why we have negative x for the reactants and positive for the products. So at equilibrium, I know that if I'm going to change by a factor of x, at equilibrium I'm going to have 0.11 minus whatever that change is. Same thing here, 0.144 minus x. And then obviously for my products, that's not going to change because I started at 0, so I'll just have positive x. Okay, so hopefully that makes sense, because one of the biggest part is being able to properly set up your ice table, because if you set that up, then you ruin the whole question. Okay, so make sure that you really understand that. So now we're going to set up, remember the equation we learned yesterday where we had to do products over reactant in order to solve for the equilibrium constant. So we're going to say that I'm going to say EQ today. KEQ is equal to, remember, products over reactants. So let's plug our products in, because they're going to go on top. So we're going to have COCl2. And then we're going to divide that by our reactants. Remember, if we had any coefficients in front, which we don't in this case, they all have 1 mole, we would put that as the exponent. So in this case, we don't have any exponents. We're just going to leave it like that. And now it's a matter of subbing in our concentration values at equilibrium, right? If we're trying to find the constant well, we know the constant equilibrium. If we're trying to solve for x, we want to put in our values for equilibrium. So we know, based off of the equation, right here, the equilibrium constant. So this would be your K EQ. We're not going to solve for KEQ this time like we did yesterday. Now we're going to use that to help us solve for X. So in this case, our K equilibrium is 0.20. So we can substitute all of our values in that we know. So I know that I have 0.20. My concentration of my product is going to just be X, right? I'm getting that from the table above to the right. And my carbon monoxide is 0.11 minus X. And my chlorine is 0.0144 minus X. Okay, so you'd set it up like that. And now our goal is to make it so that it matches our quadratic form like this. So we want to put all of our x squareds together, all of our x's, and all of our regular terms together. So let's go back and set that up. Okay. So the first thing you want to do with this is multiply. We're going to have to factor through these ones. So remember that if we multiply these two here, this has to multiply times this as well as this. So a little bit of going back to some more math. And we multiply this times this. So let's do that first before we do anything else. So we're going to have 0.20 is equal to X. And then on the bottom, after we factor all of that through, so I'm going to do 0.11 times 0.0144, and I end up with 0.001584. Obviously, 0.11 times negative x is negative 0.11x. And then the same thing for 0.0144x. And then at negative x times negative x, you get a positive x squared. Okay, I'm going to do a lot of steps just to really break it down for you and make you understand where the numbers are coming from. If you do the quadratic formula and you do most of the steps in your head and you still come to the right answer, you're not going to lose marks. I'm only doing this to really break down each single line for you to figure out where things are coming from and you don't get lost. At this point, I want to get all the like terms together, but I want to get this out of the denominator here. So in order to bring it to the other side, I'm going to have to make it be, it's division on the right hand side. So when I bring it over to the left hand side of the equation, I'm going to have to multiply it times 0.20. So now I'm going to have 0.20 times 0.001584. And now I can actually put these like terms together, so I can put those x's together. So if you put that in your calculator, you end up with 0.1244x. And then I still have my x squared. And now this is equal to x. So I'm going to set it up like this, actually, so you don't get confused. So this is 1, 2, 3. At this point, now I want to factor everything through again. So I'm going to take that 0.2, multiply it by this term, and by this term. So if you multiply that all through, you end up with 0.0003168 minus 0.02488x plus 0.20x squared. And that is still equal to x. So now, at this point, we want to bring the x to the other side. Okay, so you always want to make it equal to 0, right? Just like we did over here. Right, so the value has to be equal to 0, so we need to bring that x over to the other side. So let's bring x over to the other side, and we end up with 0.000318. If it's positive x on the right, we bring it over to the left-hand side, it becomes negative. So we have negative 0.02488x plus negative 1, so you end up with negative 1.0248x plus 0.20x squared, is equal to 0. So now we've set it up, so this would represent your C, this would represent your B, and this one would represent your A. So now you have everything you need to plug into your quadratic formula. So I'm running out of room. I'm actually just going to extend the page so that we have more room. So if you're running out of room, maybe you want to get another piece of paper. So remembering our quadratic formula, I'm going to rewrite it out for us. X is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. Okay, then it's a matter of substituting our values in. Let's see here. So we have x is equal to negative 1.02488 plus or minus the square root negative 1.02488 squared minus 4 times my a, which is 0.2, and then my c, which is 0.000318. We're going to take that whole thing and we're going to divide it by 2 times 0.2. Okay, then x is equal to, if you have two negatives, obviously this would become a positive, so 1.02488 plus or minus the square root of, so if you put that in your calculator, you end up with, if we take the square root of this, you end up with 1.05038, and you're going to subtract 4 times 0.2 times 0.00318 will give you negative 0.0025344. It's good to keep a lot of digits. Like if you can put that all in your calculator and get the right answer, that's good. But if you're writing it out step by step like I'm trying to do for you, it's good to write out a lot of digits just so you don't kind of shortchange yourself when you get to the end. Okay, again, all of that, if we take 2 times 0.2 is going to give you 0.4. So this would be, well, when we start doing the quadratic, this would be step 1, this would be step 2. I kind of put them on top of each other, but hopefully you guys have organized yours better than I have. I just know I'm running out of space, so I don't want to have to squish things when we get to the end. Okay, so at this point now I'm going to subtract those two under the square root, and then I'm going to take the square root of it. So I'm going to have x is equal to 1.02488 plus or minus, and if you subtract those two and you take the square root, you end up with a value of 1.02476. All of that divided by 0.4. So now you have to take two x values. Because I have the plus and the minus here, that's going to give me both values. So I have to find an x for both the positive and the negative. So if I find the positive x, so I'm going to put 1.02488 plus 1.02476 and divide it by 0.4, I end up with a value of 5.1241. If I take the negative x, so I do 1.02488 subtract 1.02476, and then I divide that by 0.4, I end up with a value of 0.00012. So at this point, you need to decide which of the x values makes more sense out of the two. If you ever get a value of a negative x, then you know for sure that that is not the x you should be using for the equation. But in this case where you have two x's that are greater than 0, you're going to look back to your original ICE table. So if I take 5.1241 and I plug that into my ICE table over here, if I put that into here, 0.11 minus 5.1241, I'm going to end up with a negative value. Right? And I can't have product that's not there. Like I can't go in the negative value of a product or of a reactant. So if it's gone, it's 0. I can't have negative what I already had to begin with, right? So if you get a value that gives you negative when you substitute that x back in, you know that that one's not correct. But if we take the other value and plug that one in, then you'll see that it works out. Right? So if we wanted to put in the concentration of carbon monoxide, we have 0.11, which before was minus x. We're going to substitute the x value, 0.0012, and you'll see we end up with 0.1088. So at equilibrium, carbon monoxide will now have a concentration of 0.1088 moles per liter. We're going to do the same thing for our chlorine. So chlorine we had 0.0144 to start with. We know that our change was 0.00012. So if we subtract those two, we end up with 0.01428 moles per liter. And then and we do our product, which is 0.00012, right? Which is just what our x value was. So literally all I'm doing is taking the value that we got right here and substituting it in for my x's that I denoted right here, here, and here. And that would be the final step to your answer. So you would get marks for putting those in. Make sure that you read the question properly. Sometimes they just ask you for the value of x, and some questions want you to take that x value and substitute it back into your ICE table that you created originally. Okay, so make sure you really pay attention because you will lose marks if you don't have it plugged right back into the original ICE table. So looking at this, you'll see there's a lot of work to this question and a lot of opportunities for error. Okay, you do the ICE table wrong right off the bat, everything else is not going to work out. If you make your equilibrium equation incorrect, maybe you put reactants over products, the whole thing shot out the window. Then look at how many negatives, and negative times a negative makes a positive. You got to take a square root, make sure you do the plus or minus. And all of that you can just see where there's a huge chance of mistake. So for me, it helps if I do little steps by little steps. Some of you might want to just put in your calculator, but I promise you there's a huge chance of error when you do that. Okay, so just be really careful and always go back and double check your answers to make sure that you get the same answer every time. Sometimes you can do these questions, they'll be a little bit faster. But you have to do a little check before you do these questions. And in order to do that, you'll see it's mentioned on the other page, but I just kind of want to do it for this question. That if you want to know, sometimes this x could be negligible, meaning that it's so little that really the change is not going to make a difference in the actual final concentration equilibrium. So then you can get rid of all the x's at equilibrium where they're on the reactant side, which makes the question a lot more easier, which makes it so you don't have to do quadratic. So if you want to test to see if you need to keep the x or you can get rid of the x, you're going to take Okay, so if you take the smallest initial concentration and you divide it by your K, your equilibrium constant, and you get a value that is greater than 500, then you're happy. You don't have to keep those x's, that they're negligible. The change is so small that it's not making a difference. If you divide those two and you get something less than 500, then you know you're probably going to have to do a quadratic, and you're going to have to keep the x value because it is actually making a huge difference in the change. So for this question, if we were to substitute the smallest concentration, so out of these two, obviously chlorine has the smallest concentration. So we would substitute 0.0144. We divide that by our K, which is 0.20. And if you put that in your calculator, you'll see that it actually has a value that is less than 500. So we have a sad face. And we actually have to do all of the equation with the x. Like I said, you'll see more in our next unit, or more in chapter 8, that you'll see we'll have a lot of questions that are actually greater than 500, not so much in chapter 7, but in chapter 8 for sure, you'll see where we have a lot of questions where if x is greater than 500, you can just get rid of it, and makes the question that much easier. But for chapter 7, I'm sorry, you're going to have to do a lot of work. But keep that in mind. Okay, we do need to finish the rest of the notes, so we'll go back here. So we also have to look at qualitative interpretation. So when K is greater than 1, so again, we're looking at that equilibrium constant, products are favored. You need to memorize this. Greater than 1, products are favored. If K is approximately equal to 1, then we're basically at equal concentrations of reactants and products, and we're at equilibrium. When K is less than 1, reactants are favored. So really key, if it's greater than 1, it's going towards the products. If it's less than 1, the reaction is going towards the reactants. And this part right here at the bottom here, where it says when Kc is small compared with the initial concentration, the value of the initial concentration minus x is approximately equal to the initial concentration. Thus, you can ignore x. And this is what I was just talking about a minute ago. If the initial concentration of a substance is 0, any equilibrium concentration of the substance, no matter how small, is significant. In general, values of Kc are not measured with accuracy better than 5%. Therefore, making approximation is justified if the calculation error you introduce is less than 5%. So this is where we have our smallest initial concentration divided by our K has to be greater than 500 in order for x to be negligible. Okay, so let's do the last part of the question on the other side. Okay, so this is from page 349 in your textbook. Consider the reaction of carbon monoxide and chlorine to form COCl2. At 870 Kelvin, the value of Kc is 0.20, and at 370 Kelvin, the value is 4.6 times 10 to the 7. Based on only the values of Kc, is the production of COCl2 more favorable at the higher or at the lower temperature? So we know at 870 Kelvin, we're going to get a Kc value of 0.20. At 370 Kelvin, we're going to get a Kc value of 4.6 times 10 to the 7. So our goal is we want to have more production that is favorable of our products, right? Remember, this is a product that we're forming. So let's go back here. We just learned if we want products that are favored, we want to have a K that is greater than 1. So let's go back. Which one of these two has a K that is greater than 1? So this is greater than 1, however, it's really, really small and close to 0. So that'd be approximately at equilibrium. So this one, our K is way greater than 1. So therefore, products are favored. So to finish this off, says based on the values, which one would it be favorable, higher or lower temperature? So favorable at the lower temperature. All right. See you guys later. That's it. Have a good day.